For close on 200 years, British craftsmen have worked ceaselessly to build up the tradition which has made British steel a hallmark the world over for the finest and truest steel. Reaching the peak of quality in the crucible process, tool steel is now the key to modern manufacture. But crucible steel provides a mere fraction of the vast quantities which industry consumes each year. Throughout the country, a network of factories depends on the continuous supply of an ever-widening range of raw steels if they are to meet the demands of the home market and the world's heaviest export trade. From the first crude steel of the 18th century has come a multitude of new metals, steels to make anything from a watch spring to a battleship. The high standards set by the engineer of today has created countless new steel research laboratories staffed by leading specialists. Intricate instruments have been devised for testing and measuring, leaving nothing to chance. Safety margins are always ascertained and provided by testing a sample of each new alloy to destruction point. Still other instruments have been invented for measuring in terms of parts of a millionth of an hardness, dimensions and contours of finished steel products. But a finish of such high precision is only possible with fine steel, and behind it lies the story of the making of British steel. Our story opens among hills and farmlands, where excavators stripped a layer of topsoil, uncovering the seam of iron ore which has lain for centuries beneath the earth's crust. First step to the making of steel is the manufacture of iron. Mechanized shovels bite out the ore, tons at a time, and load it into railway wagons for transport to the steel works. Iron ore is not solid metal, but a heavy, rock-like mineral. Only a small part of it is iron. The rest consists of impurities in the form of silicon, sulfur, and oxygen. The outside of the steelworks, with its disordered tangle of towering structures, hardly indicates the inferno of noise, heat, and flame that lies within, night and day. To its marshalling yards come trainloads of iron ore, limestone, and coal. Coal, vital to steel making, is fed into rows of coke ovens and heated to extract the byproducts. What remains is coke. When the heating is finished, a ram which travels up and down the line of ovens comes into position. The oven door is removed and the end of the ram is set against the opening. As the ram begins to push, a flaming wall of red-hot coke emerges at the other end. Hot coke is collected in a moving wagon, in which it is carried away to be quenched by water. After quenching, the coke is taken on a conveyor belt from the coke ovens to the blast furnaces. Skips, or small trucks, take the coke, limestone and iron ore up to the top of the furnace, where it is mechanically fed into the blazing interior. Inside the furnace, a blast of hot air roars through the charge, slowly reducing it to a bubbling, seething mass. The metal sinks to the bottom of the furnace, while the impurities form into a slag above the metal. After this slag has been run off, the furnace is tapped and the molten iron flows through channels into large ladles. After tapping, a pneumatic gun blocks the tapping hole with a charge of fire clay. Ladles of hot metal travel to the Bessemer plant, where the iron will be converted into steel. Fastest of all the methods of making high-grade steel is the Bessemer converter process. A crane brings up the ladle with its 60 tons of molten iron. This is emptied into the converter, a large steel cauldron through which cold air is forced under pressure at 45,000 cubic feet a minute. The whole process, from charging the converter to tapping, takes only 18 to 20 minutes, so timing is vital, calling for the utmost skill and speed from the Bessemer crew. Captain of the crew is the chief melter, on whose judgment the quality of the steel depends. To his experienced eye, the changing color of the flames at the mouth of the converter tells the story of the chemical changes going on inside. According to the type of steel required, alloys such as chrome, molybdenum or tungsten must be added to the charge together with steel scrap. The compressed air blast is turned on again, and the converter goes up for the final blow. Now every second is of importance. A sample of the steel is taken so that the chief melter can judge whether the charge is ready for tapping. The color changes taking place in the sample ladle show that the converter holds a charge of first-class steel. He gives the signal to pour off the slag, which must be run off before the pure steel can be poured out. Slag ladles are taken to the disposal beds, where some of the slag will be turned into fertilizer and other byproducts. in the Bessemer plant, the tapping ladle is brought up to receive the charge of liquid steel. Some of Britain's finest steel is made by the electric arc process, where the melting is done by high-tension electric current flowing through carbons to the charge in the furnace. At various times during the melt, samples are taken. When the sample cools, drillings go to the laboratory for analysis. Here, the knowledge of skilled scientists combines with the steelworkers' practical experience to make possible a wide variety of new alloy steels of ever greater tensile strength and quality. In a matter of minutes, a full chemical analysis of the sample is ready, and the information is passed on to the chief melter. These facts enable him to carry out any modifications necessary to bring the charge in the furnace to the exact specifications required. One of the finest methods of making high-grade steel in large quantities is the open hearth process. A mechanical charger runs up and down the line of furnaces, feeding each in turn with pig iron, limestone and steel scrap. The inside of the furnace is like a huge oven, lined with fire brick and heated by a blast of flaming gas, which sweeps across from one side to the other. In addition to the samples which are sent to the laboratory for analysis, a strict control is kept of the temperature of the metal. For this purpose, a pyrometer is used. A thermometer on the end is dipped into the liquid steel while the operator takes his reading from the delicate recording instrument. As the time for tapping the furnace draws near, final additions of alloys are made. The steel is on the boil. The last laboratory report shows that the charge has reached the required specification. The furnacemen begin to ram through the tapping hole at the back of the furnace in order to release the molten metal into the waiting ladle. The climax of 14 hours of skillful nursing and care devoted to the making of 80 tons of the world's finest steel. bulk of Britain's steel is made into ingots, varying in size from a few hundredweight to 250 tons or more. The molten metal is poured into cast iron ingot molds. A large quantity of steel is also used for making castings. These may be anything from a small frame or bracket to the 300 stern plate ocean liner. As soon as the metal becomes solid, the molds containing the ingots are brought to the stripping bay where the molds are removed. Ingots are the basis of steel production. They can be rolled or forged into billets, blooms, bars, slabs, plates, rods, wheels, girders or tubes, into any of the wide range of semi-finished products which feed the world's engineering shops. Before the ingots are rolled, they are reheated to the right temperature in gas-heated chambers known as soaking pits. When the ingot reaches rolling heat, it is picked out of the soaking pit and placed on a chariot which carries it to the rolling mill. A trained crew operates the mill. Silent and intent, almost a part of the machinery, they work the levers which control the movements of the ingot and the pressure of the rolls. Here, speed and precision depend on teamwork of the highest order. In less than 2 minutes, the 2-foot thick ingot is rolled out into a 7-inch thick bar. As the bar leaves the main rolling mill, it is carried through a deseamer, which removes any scale or blemishes that may have formed on the bar during the rolling process. The bar now passes through a battery of finishing rolls, which further reduce its thickness to 2 or 3 inches. As it emerges from the rolls, a guillotine cuts the 150-foot bar into shorter lengths. As these reach the end of the line, they are stacked on a conveyor which takes them to the final inspection bay. High-speed strip rolling produces the tin plate and sheet steel which goes into motor car bodies, belt buckles, tin cans, radio components, and 1,000 other light steel products. The scale which forms on the surface of the slab during reheating is blown off by a high-pressure spray of water. The 8-foot slab then passes through a series of rolls, each of which successively reduces its thickness and increases its length. Here again, close supervision is called for, and the human element is vital. At the electrical controls in the pulpit, nerve centre of the mill, the operators keep a watchful eye on the racing strip, always within reach of the emergency button, which will sound a warning and bring the mill to an immediate stop. Failure to ensure perfect synchronization of the varying speed of the rolls would result in what is called a cobble, 400 feet of red-hot steel strip, running wild. As the strip emerges from the final rolls, at 2,000 feet a minute, flying shears cut it into pieces of the required length. Sometimes the shears are raised, allowing the strip to be wound into continuous coils. Among the many uses of steel strip is the manufacture of piping and tubing. Here the flat strip reaves the reheating furnace and passes between rollers which form the hot steel into a tube, welding the edges together, after which a circular saw cuts it into the required lengths. To meet the demand for constructional steel, Britain supplies thousands of tons of girders, joists, rails and other sections to all parts of the globe. Pit arches for mining, jibs for cranes and derricks, beams for buildings, ships and bridges, for everything that calls for a combination of lightness and high tensile strength. The world's railroads and shipping call for a constant supply of steel plates for shipbuilding and locomotives. Slabs, which have been made from ingots, are brought from the preheating furnace to the rolling mill by a mechanical charger. An indicator shows the gauge at which the plate is being rolled, enabling the foreman and his crew to work to fine limits. The same steel is rolled into tires for locomotives and wagons, which carry goods and passengers across distant continents, through the dry lands of Africa, by Indian trails, and the high passes of the Andes. Some ingots are rolled into armor plate for tanks and battleships. The scale which forms on the surface of the slab is removed by throwing on branches of trees. As the slab passes beneath the pressure rollers, the boiling sap from the wood explodes and blows away the scale. drop stamp forge, billets of alloy steel are pounded into semi-finished parts of complicated shape. Engine components, crankshafts, valves, gears and axles, which must stand up to high working strains, are all products of the forge master's craft. Some of the world's largest ingots are forged into boiler drums, marine shaftings, turbine housings, and other large one-piece jobs. The gas-fired reheating furnaces are controlled by pyrometers and can take monster ingots weighing up to as much as 250 tons. This ingot will be forged into the high-pressure boiler drum of a Russian superpower station. Overhead cranes take the ingot to the giant 7,000-ton press, the largest of its kind in the world, where it undergoes a series of forging operations. Dwarfed by the towering press stands the forge master. His experienced eye enables him to work to specifications calling for a finish calculated in thousandths of an inch. By quiet gestures, he gives split-second orders to his operators who manipulate the press and the two 250-ton cranes which revolve the ingot. Britain is proud of her steel industry. From the great record of output, quality and close understanding between workers and management has grown her name as producer of the world's finest steel. The making of this steel is something more than a skilled craft to the Jim Browns of Sheffield, the Jock MacDonalds of Clydeside and the Ben Evanses of South Wales. To them, it is part of a long tradition, worthy of the generations of craftsmen who have dedicated their lives to steel, tough as these men who make it. An inspiration to the coming generation who will carry the flaming torch of Britain's steel industry, making steel for the ships that plough the seven seas, steel for the planes that race across the skies, steel for the bridges and houses of a world at peace once more, steel for the new life of tomorrow that will reward the people of today.